This lesson is about the law of sines. Before we get into that, let's take a look at a right triangle. We've done problems like this where we were asked to solve the right triangle, and that just meant find all the missing sides and the missing angles. We also have to be given that. Okay, so given this information, I have a 90-degree angle, I have a 25-degree angle, and I have the hypotenuse is 4. I can start by filling in the missing angle measure that would make this add up to 180 degrees. So I know that A equals 65 degrees. In order to solve for side B, I'm going to relate the angle that was given and the hypotenuse with that. Well, B is opposite 25 degrees and 4 is the hypotenuse. That means that sine of 25 degrees equals opposite over hypotenuse, as in SOHCAHTOA. Solving this equation, B equals 4 sine of 25 degrees. So B is approximately 1.69 units. I can go through a similar process to get side A. The relationship between 25 degrees, the hypotenuse, and A. A is adjacent to 25 degrees. SOHCAHTOA, that means cosine of 25 degrees equals adjacent over hypotenuse, or A over 4. So A equals 4 times cosine of 25 degrees, and A is approximately 3.63 units when we punch that into our calculator. So this is just a quick review, recognizing that we can solve any right triangle using your trig function, sine, cosine, sometimes tangent. And now we want to take a look at other triangles, because obviously not all triangles are right triangles, and we'd like to be able to solve acute and obtuse triangles as well. I'm going to ask you to focus on different parts of these triangles, and this is going to help us derive the law of sines. So let's begin by looking at triangle ADB in both triangles. ADB, this triangle right here, and over here ADB, this triangle right here. Something I can say about those triangles is that sine of A equals H over C. Sine of A, sine is opposite over hypotenuse, H over C. And that holds true here as well. In this triangle, sine of A, opposite over hypotenuse, H over C. So this holds true for both triangles, the acute and the obtuse triangle. Let's now focus on triangle BDC. In the acute triangle, BDC is this portion over here. And I can make the statement sine of C, sine of angle C, sine is opposite over hypotenuse, is H over A. Triangle BDC, in this triangle, BDC is actually the whole thing, including those dotted lines. So in triangle BDC, sine of angle C, opposite is my H, hypotenuse is my A. Yes, so that is still H over A. To derive the law of sines, I'm going to take both of these equations, which hold true for both triangles, and I'm going to isolate H. So over here, I'm going to multiply both sides by C, and I get H equals C times sine of A. Over here, multiply both sides by A, and I get H equals A times sine of C. Well, because H is in both of these, I can use my transitive property and say that these two expressions must also be equal. So C times sine of A equals A times sine of C. Manipulating this algebraically just so that it looks a little bit nicer, if I divide both sides by C, then these end up canceling. If I divide both sides by A, then these end up canceling. And I can rewrite what I'm left with as sine of A over side A equals sine of C over side C. This is the first part of the law of sines. Your book gives it to you as A over sine of A equals C over sine of C. Both work. You can just flip those ratios and that's fine. So, the full law of sines looks like this. In any triangle, obtuse, acute, right, doesn't matter. Sine of an angle divided by the opposite side is proportional to sine of any other angle divided by its opposite side. This is the formula that will allow us to solve any triangle, not just right triangles. So let's take a look at this example. It's in your book on page 282, number 9. We are given two angle measures to start and one side length. Okay, let's start by sketching out a picture of this. Just draw a generic triangle. Label side A, or angle A, B, and C. And I know angle A is 68.41 degrees, angle B is 54.23 degrees, and then the sides opposite, I have A is 12.75, so this is just side C and this is side B. I can begin by adding these up and subtracting from 180 to get the measure of the missing angle, C, as 57.36 degrees. Now the first thing we want to notice is what combination we have. We always want to look for an angle and its opposite side. In this case, I have that pair. If you don't, this may be an ambiguous case problem, which we'll be getting into in a couple days. But I have this pair, so that means that I can go back to my law of sines and plug in. So I can say sine of 68.41 degrees over 12.75 is proportional to, and I have this angle measure, so I can say sine of 54.23 degrees over side B. Solving this equation, B equals 12.75 times sine of 54.23 degrees divided by sine of 68.41 degrees. When I punch that into the calculator, making sure I'm in degree mode, I end up with B being approximately 11.13 feet. To solve for side C, I can take this same ratio, sine 68.41 degrees divided by 12.75, and now I'm going to set it equal to the relationship between angle C and side C. I found that angle C was 57.36, so I can say sine of 57.36 degrees over, and side C is what I'm looking for. Then to solve, C equals 12.75 sine 57.36 degrees divided by sine of 68.41 degrees. Punching that into the calculator, side C equals 11.55 feet. So I found the missing angle, and I found both missing side lengths. And that's how we use the law of sines for any triangle.